Hi everyone, Shalom לכולם. אני Eli Arbel from IBM Research Lab in Haifa. I'm very happy and excited to be here. And first of all, I would like to thank the organizers for having us here, giving us the opportunity to take part in this event today, and hopefully maybe eventually becoming a more integral part of this community. A word about myself. I'm 15 years with IBM in the Research Lab in Haifa, as I said. In the last 6 years or so, I'm in managerial roles, managing groups. Now I'm managing the quantum activity in Haifa. And I'm here to give you a brief overview of what we do. I've chose maybe the main topics that we've been working on in the last 2 or 3 years. Let me start by visually introducing the team, the people who are also here, part of the research team in Haifa working on quantum. People coming from physics, math, and computer science background, each with their own mixture. We're part of a global team in IBM who's responsible to building the IBM devices, the computers, and the software stacks above it, which allows people to use the devices from the cloud, as probably some of you know. Our focus in Haifa is in characterization and quantum circuit simulations, which map into the software area, if you look at this as the software area, to two of the 4 components of what is called KISS-Kit, Quantum Information Science Kit. And eventually our research work, its results goes into there. And this is an open source component or package that you can all see our things that we do and use them on the real device or on quantum simulators. So 5 topics that I want to cover today. The first 4 are in the area of characterization, and the last but not least, quantum circuit simulator. And again, it's going to be a very brief overview. We have 4 posters here which are covering in more details 4 of the topics that I'm presenting here, and this presentation is kind of a trailer for the posters, so any in-depth discussion which you want to continue, which go beyond the question that maybe we'll have at the end, we have people here to address and talk in more details. So we'll start with quantum tomography, one of the topics that we work on. I guess many here know what it is. Essentially, it's a method to know what's going on inside a quantum system. There are several methods to do that. Let's concentrate on state tomography, just as an example or a way to exemplify one type of work that we do in the labs. So here we want to extract the density matrix of a quantum system by using a set of experiments or measurements. So again, many people here maybe know this, but I'm explaining this very quickly for those who are not. And there are some assumptions here. We should be able to bring the system into some state. Very quickly, we have this density matrix here that we want to find. We can measure the state in various bases and get, for example, the probability to get 0 under the x basis, to get 1 under y, etc. And if we do enough experiments like this, we get here the probabilities of getting the outcomes based on each of the bases. And if we use what is called a tomographically complete basis set, we can eventually, with some mathematics, extract the density matrix. So we have the probability here, so it's a vector of numbers. And these are basically the projectors based on Born's rule and spectral decomposition. This is a not square matrix. We can turn it into a square matrix, do the inversion, and isolate rho. The errors here are vectorized notation, which are kind of an implementation-oriented way to putting this together. In an ideal case, this would probably work, and we'll get a valid density matrix. But with noise, usually this is not the case. And instead of doing linear inversion, we have to turn it into an optimization problem and solve it with maximum likelihood estimation method. There are several, like least square or convex optimizers. Basically, we're minimizing this term, wanting it to be 0 under constraints. This should be Hermitian, positive semi-definite, etc. So one type of our work is to take results like this, understand them, make them available in the IBM offering, work with them, using them for characterization, etc. And then also further enhance them, working both on the theoretical aspect of the topic as well as practical aspects of the topic. And we do work on several other types of tomography, like process, gate set, etc. Gadi here as a poster, and he can talk in more details later for those who want. Another characterization method is randomized benchmarking. This is an efficient method in the sense that it scales quite nicely in the number of qubits, unlike some of the tomography methods, which requires basically a lot of experiments. This one scales more nicely, and it's robust. It's less sensitive to, or not sensitive at all actually, to spam errors, state preparation and measurement errors. Essentially, the idea here is to prepare a sequence of gates or operators to run on the device. Here we choose from the Clifford Group. I'll talk a bit about this in the next slide. We have here M operations, then the M+1, the last one, basically reverses back the computation such that we expect to get to the state from which we started. We start from psi, we expect to get to psi after this M+1 sequence, and this will work in an ideal case. We have noise, so in practice it doesn't work. So as a way to characterize the noise we have, we do a lot of experiments with these kind of sequences. We generate a lot of sequences in different lengths. And here we have this graph where the x-axis tells us the Clifford length that we use, and the y-axis is the probability to get back to the initial state. So very short sequences will have high probability to get back to psi. And then we have this collection of results. As the Clifford length increases, the probability drops down, and this is basically an exponential decay that we expect to see. And after experimenting and measuring the results of such sequences, we obtain the collections of probabilities and feed them into this expression. And from it, we can extract alpha, which gives us the average gate error or error per Clifford. So this is another way to characterize the system from gate error perspective. A word about the Clifford Group. For those who know, it's a unitary 2 design. It brings, basically it means that it brings very nice properties to randomized benchmarking, the robustness to spam errors, as I mentioned, ability to select random elements from the group to build this sequence in a uniform way. All those properties, if you want to simulate it, there is a polynomial algorithm to do that. It's a very nice group from randomized benchmarking perspective, but it also grows very fast in the numbers of qubits. So there are questions here that are related to if you are going to do randomized benchmarking for many qubits, now many, maybe 3, 4, 5, or in this ballpark, or even more at some point. How can we choose efficiently the next element from the group? And other areas that we work on in terms of research in this subject is generalizations of the basic randomized benchmarking that I've described, like interleaved, where we put non-Clifford gate or specific gates in between the gates there in the sequence, using non-Clifford groups, actually. And again, on this, we have a poster that Shelley can talk in more details later on for those who are interested. OK, another characterization topic that we work on is the characterization of maybe more known or common parameters like T1, T2, T2 star, etc. The amplitude damping, if you like, phenomenon. And this is something that we do regularly in IBM. I mean, we evaluate these parameters on a regular basis, maybe on a daily basis, because those parameters change. There is drift. We publish these parameters. We use them to calibrate the machinery around the device. And since those devices are being used by users, company, researchers, etc., us in IBM, we want to minimize the time we spend on this process, which basically means that once, while we do that, the device is not available. It's basically a downtime, right? And it eventually translates to some extent to how many experiments we need to run on the device once we estimate the current T1, for example, I'm talking here on T1 for example, such that the downtime is minimized, okay? So what we did in our team is we took principles from estimation theory, specifically Fisher information, which is a metric that, given a probability function, right, this is the exponential decay that we can treat as a probability function. Given a probability function, we want to estimate by way of sampling, and that function depends, for example, here on one parameter. It gives us this metric gives us information about how much information we can extract by way of sampling specific value of theta. Theta here is the parameter of the probability function we want to estimate. So here we have the exponential decay of T1, and it depends on 3 parameters. Actually, empirically, we found that A and B are quite stable. And we need to more regularly or more frequently evaluate T1. So if we treat this expression as 3 single parameter estimation problems, we can write a Fisher information expression for each of those. This is for T1, this is for A, this is for B. And eventually we want to maximize this expression in order to get the best T, the best time here to measure such that it will give us the highest degree of information, right? So instead of measuring T in different locations, starting from 0 immediately and then spread the points, I don't know, over the time of 40 or 5T, this gives us a framework that tells us that you can measure only at 1 point of this small t, given A and B. And more than that, it actually gives us where to measure. And by way of this, we can reduce the number of experiments. And it can be generalized and exploited, this kind of approach, to other parameters like those that I mentioned, T2, T2 stars, and even randomized benchmarking, which we saw.
Isn't P normalized?
P is that expression. It's that expression, yeah.
So how can it be normalized if B is different from 0? I mean, the integral over P over dt must be 1, or I misunderstand the...
I'll let Yuda here take this, because he's been working on it actually, so it's the most...
B is actually the measurement error. You can take it, I mean, officially it can be 0, we can discuss later. But it just take it as the measurement error at the end. The probability to be either 1 or 0 is normalized, of course.
You'll explain it.
Great, good, okay. Yeah.
About this slide?
This one?
Yeah. So if you're trying to estimate T1, then the optimal time to sample this curve is a function of T1.
So
how do you address that?
Yeah, so it's a good point, and I probably have been mentioned this. We take empirical T1 results from previous measurements, and then we refine them, okay? We measure them again. So we are not starting from 0 knowledge. We have some prior knowledge of T1. Again, this is something that changes, along a period of time, but we can rely on previous results to make it more accurate in the current measurement. All right. Another thing that we work on, quite recent topic that we started to work on, and it goes back very nicely, I think, to Eyal's presentation. We look at dynamics of a quantum system, its evaluation over time. And as we saw earlier, we can describe it as using Lindblad expression or a Lindbladian, which is comprised of 2 terms. The Hamiltonian, which is related to the coherent part, and this term called dissipator, as we saw, which is related to the noise. And this one contains parameters that we don't know. Here we have terms over single qubits and 2-qubit relations, etc. And what we are trying to do here is to estimate the parameters of the noise, as well as relationships between the pulses that we use to drive the system over time, which affect eventually what we see here in these 2 terms. And again, I'm not going to get into too much details here, but the approach that we're taking is a combination of experiments, measurements, again, and a classic part, simulation on a conventional computer, which tries to explain the results that we see experimentally by way of estimating the parameters. Last topic I'm going to touch is not in the area of characterization, it's quantum circuit simulation. Qiskit has several quantum circuit simulators. It's basically a set of classic algorithms that you run on classic or conventional computers to simulate your circuit. And there are several approaches, several representations to how to do that. One basic one, very well-known one, is that of a state vector representation. You give an amplitude for each of the the basis vectors. And this results in an exponential representation and also, of course, runtime. And there is a limit on the physical computers that we have today, how much of this we can host. I don't know, I think 56 or 57 maybe today. In the matrix product state simulator, we represent things differently. We have a 2D matrix, if you like, or a tensor for each qubit. Essentially, it's two matrices, one for each of the qubit basis. These are the gammas here. So we have n tensors for n qubits, and also lambdas here in between the tensors, which in a way describe the relationship between the qubits. We can construct the state vector out of this by multiplying the tensors. We can do quantum circuit simulation here. When we do quantum circuit simulation, we see mostly single qubit gates or operators, or 2 qubits, something like that. And this translates nicely to exploiting the locality of the circuit simulation that we have by way of simulating or calculating the effect of the operator on the tensors. Okay. So a single qubit gate will result in some operation of the corresponding qubit tensor. 2 qubits will work on 2 tensors. There is some kind of constraint here that if we have 2 qubits, we need to have them consecutive in the data structure. So we need to do swap operations to bring them together. And then if we take this type of simulation and compare it performance-wise to other types of simulation, more classic, if you like, or direct, like a simulator that uses this kind of representation, then we see this kind of behavior for some type of circuits, and I will disclaim it in a bit. Here on the x-axis, we have the number of qubits that we want to simulate, and we use here some kind of random circuits that we generate with some probability of how many CNOT gates and other types of gates. And the y-axis is the time. So we see here that the red curve, which is related to the state vector simulator, just flies exponentially up as a relation to the number of qubits, while the MPS simulator much more scalable. And again, this is a very good example for MPS. There are other examples which are bad for MPS in the sense that we see that its performance is as bad or not good than the classic way of simulating things. But again, the idea here or motivation is that there may be problems for which this type of simulation will give us better performance on the classic computers. So these are the areas that we work on in terms of research when it comes to MPS. For example, how to efficiently compute the expectation values without reconstructing the state vector. Our implementation is accurate in the sense that it keeps all the information, so we can reconstruct the state vector. Maybe we can do some kind of an approximation simulation and still keep the most important part of the information, if you like. For example, getting rid of very low or below some threshold Schmidt coefficient in the lambda matrices. How can we take a quantum circuit or set of operations and decide upfront whether it's suitable for MPS or not? Hint, there is a relation to the amount of entanglement and the type of entanglement. And also here we have a poster by Merav, which can be used to elaborate more later on. So that's it. Thank you very much.